So with water, water is going to be familiar for all organisms that we know of and think of as alive. Anything that we know of as life on Earth is going to be pretty much dominated by having water in its environment. Even if you live in a desert, water still plays a role in your world in there. You just have learned to conserve water really well to live in a desert. Water can exist as gas, liquid, and solid on Earth, and it's going to participate in reactions to sustain life. 70 to 95% of cells are going to be made up of water, and it's going to surround a lot of cells in your multicellular organisms. So it's got this polarity where it can make these hydrogen bonds that we talked about, where you've got that partial positive and partial negative in there. And that's going to give water a lot of its properties in there. So a lot of this we've already talked about in here. The cohesion, it allows it to hold water together. It's also going to allow it to move water against gravity in plants. So if you've ever looked at a plant and you go, okay, the leaves are all wilting. I'm not real good with plants indoors. And the leaves get really wilty when you don't water them. And you can put water in there, and with some plants the leaves actually kind of spruce back up and come back to life if you don't wait too long to give them the water in there. But the water goes from the dirt up to the top against gravity. And what allows it to do that is that cohesion in there, where it will hydrogen bond to the surface of the plant on the inside and allow it to move up. So adhesion is the clinging of one substance to another in there. So with plants they call it the cohesion adhesion in there, that it helps to resist gravity and allow it to move up. It also is going to give it the surface tension in there so that you can have the insects that walk on water, the bubble that forms in your glass that you fill up too much in there. Water is good at helping to moderate temperature. It can act as a heat bank where it can absorb and release large amounts of heat and only change its temperature slightly. So where you look in Western Washington, we've got the Puget Sound that's going to help keep our temperatures relatively stable over here. The temperature we have early in the morning, the temperature we have in the middle of the day, and the temperature we have at night are not huge variations in some places. So say we have, take a typical winter day here. It's early in the morning, it's 33 degrees and raining. In the middle of the afternoon, oh, we get up to the balmy 45 in there. And then it goes back to the 33 and raining. If you go over to eastern Washington or you go out to the high desert in the winter, you might have it be 15 degrees in the morning. It can be 70 degrees in the afternoon, back down to 15. Huge variations in there because they don't have the huge bodies of water that are going to release and absorb the heat in there. So it keeps the temperature fluctuations from being as big in there. And that's actually a good thing that we have a lot of water in us. It keeps our temperature more stable in there. If you become dehydrated, you're not going to be as good at regulating your body temperature in there. It's got kinetic energy in there, energy of motion. So the faster the molecules move, the higher the kinetic energy. When you heat water up, it's going to have more kinetic energy in there, and the molecules are moving around faster. When you heat it up enough, you put in enough kinetic energy that some of those molecules get so excited and they're running around that they just run all the way away from that puddle of water altogether, and they will leave, and that's when it turns into a gas in there. So the heat's going to be dependent partly on volume. If it's in a container that's holding it together with pressure, it'll get really hot in there and it can't escape. So in the back room there for the microbiology class, we autoclave things to sterilize it. And it's a big pressure canister, and it gets up to 121 degrees Celsius inside of there with the water. Water boils at 100 degrees, and then it starts to escape. You can't get water on your stove over 100 degrees. It's escaping once it gets over 100 degrees in there. But because we've got the pressure canister that holds it in there, it gets a higher temperature and has more energy in there. So temperature, there is a difference between temperature and heat. Heat is the form of energy. Temperature is a measure of the heat intensity, the average kinetic energy, regardless of volume. And heat is going to move from warmer objects to cooler objects. So when you open the door, a lot of times people go, oh, you're letting the cold air in. You're not letting the cold air in, you're letting the heat out. Heat's got more of the energy. Those are the things that are moving. They're going to leave. The cold doesn't do that. They're moving slowly. They're not going to come creeping in the door. So if you put ice in your water, it's actually going to absorb some of the energy from your drink that you put it in. It's not that the ice is releasing the cold in there. It's the heat that moves in there. So we can measure heat with calories. It's the unit of heat, the amount of energy it takes to raise the temperature of 1 gram of water by 1 degree Celsius. The kilocalories, a kilocalorie is 1,000 calories. It raises 1 kilogram of water by 1 degree Celsius. So when you look on your food, it says calories because people in the United States are afraid of it if you put kilo in front of it, but it's actually a kilocalorie in your food that we're looking at in there. So it's actually, it looks even worse if you said, okay, that candy bar's got, instead of 540 calories, now it's got 54,000 calories in there. It just is worse in there. So it's the kilocalorie on there. Joules is another energy unit in there, and 1 joule is 0.239 calories, or 1 calorie is 4.184 joules in there. You're not going to have to do that kind of conversion in here. So if you look at the energy when you buy food in another country, it's not necessarily going to have calories on the label. It's going to have the energy in joules on the label in there. We're the only ones that use the calories. And it's still a metric unit in there too, so it's just kind of a weird thing we do. It's kind of nice if you go by, you know, like you go to World Market and you get some of the chocolate in there and it's in joules. And you just ignore the little sticker that they have to put on with the calories, and you can pretend it doesn't have any. So your specific heat, water has a high specific heat in there. Its ability to stabilize the temperature. So how much heat is going to be absorbed or lost to the temperature change of 1 gram of the substance by 1 degree Celsius. So the specific heat of water is 1. So 1 calorie per gram per degree Celsius. That's kind of how stable it is before it's going to begin to evaporate. If you look at ethanol, it's 0.6 calories per gram per degree Celsius. So ethanol is going to evaporate and heat up faster than water is. It doesn't take as much energy to heat that. The specific heat of water is 10 times that of iron. So if you put a pot on the stove in there and you fill it up with water and you turn on that burner and you come back a few minutes later, the water is kind of maybe a little bit warmer than it was, but it's not hot yet. However, if you touch the pan is really hot because it's absorbed that change of the heat faster than the water does. So that's why we cook with the metal pans in there, is they're really good at transferring that heat quickly in there. So evaporative cooling, this is when the molecules move fast enough to escape and depart the liquid. So it's like when you boil and the molecules move fast enough in there and some of them just go off. But even if you're not boiling and you have water sitting out, they're still moving around. This just happens at a much slower rate because they're not moving as fast, but you do have some that get going and just right off to the surface. That's how you actually cool down when you're sweating. As that water evaporates and leaves the surface of your skin, it's taking with it some of the energy, so the skin behind doesn't have as much of the energy and it cools it off in there. So if you are just dripping in sweat where it's in big puddles on you, that's not going to be as efficient as cooling your body off as when you can actually have it realistically leave and the surface below can be exposed where it's lost that water. So your heat of vaporization is the quantity of heat the liquid must absorb for 1 gram of it to be converted from liquid to gas in there. So in order to evaporate 1 gram of water at 25 degrees Celsius, you need 580 calories of heat. It's nearly double the amount you need to evaporate alcohol or ammonia in there. So if you cook with alcohol like wine or anything like that and you're going to make a sauce of it, when you're cooking that wine, it's going to evaporate really quickly in there when you make a reduction of it in there and become thick, because that alcohol is going to evaporate. It has a lower heat of vaporization than water does. So water actually helps to insulate things as well. Ice is going to float on top of the water. So even though you can't usually see what's underneath the iceberg, it is still floating on top of the water. It's just big enough that there is a lot underneath it too. Water at temperatures above 4 degrees Celsius starts to expand. So as it cools down, it starts to shrink, but when it gets to 4 degrees Celsius, it starts going the other direction. The smallest is at 4 degrees Celsius. When it starts going the other direction, it gets bigger in there, and then it locks into a crystal lattice where they're held apart. So when you look at a body of water that's got an iceberg on it, the water that's up at the top, it's still not frozen there, but that's going to be your coldest water. That's going to be lower. That's going to be at just a couple degrees in there. The water that's frozen, because it's even colder and it started to go the other direction, has expanded. So it's less dense, and that's why the ice is going to float on the water. So water is the solvent of life. When we look at solvents, the solution is going to be the liquid that is completely homogeneous mix of 2 or more substances. So if you have a saltwater solution, you put 1 spoonful of salt in a cup of water, it completely dissolves in there, it's all homogeneous, that's your solution. Your solvent is the dissolving agent, the water in there. Your solute is going to be what comes apart or dissociates, that's your salt in there. So an aqueous solution is going to be one that uses water as a solvent. Water dissolves a lot of things, but it doesn't dissolve everything. There are some things, if you put sand in water, it's not going to dissolve in there. So when things dissolve in water, you'll have this hydration shell where the water molecules kind of form a little sphere around the dissolved ion. So if we take our sodium here and your chlorine here, you've got the water molecules that are all coming around looking for the attention here. They're all coming around here, hanging out in there. That's your hydration shell. So something that is hydrophilic has an affinity for water. Anything philic means you like it. Hydrophobic, you're afraid of it. Those are substances that repel water. And then we have the colloids that are a stable suspension of fine particles in a liquid. So you've probably seen things, the only example I can think of off the top of my head is like colloidal silver, where you've got a liquid that's got these little particles and they're not all clumped at the bottom, they're just floating around in there, even suspension all over the place. That's a colloid. Let's see how much. Okay. So these solute concentrations in chemical reactions, this is going to be important for us because we need to know how many atoms or molecules are involved to calculate the concentration. How many salt crystals did we have dissolve into that water? So we can take that to be how many grams, and then we convert it into this other unit, the mole in there. Your molecular mass or molar mass is the sum of all of the masses of the atoms in a molecule. So when you look at the molecular mass on there, that decimal point number that you saw on the periodic table, that's the mass of an element. It's your molar mass in there. It's how many grams 1 mole of that element weighs. The mole is Avogadro's number at 6.02 times 10 to the 23rd units of something. So what it means is you have in 1 mole of a substance 6.02 times 10 to the 23rd atoms in there. It's like saying I have a dozen eggs in there. A dozen eggs means you have 12. If you have a mole of eggs, it means you have 6.02 times 10 to the 23rd eggs. If you have a dozen carbon atoms, you have 12. If you have a mole of them, you have 6.02 times 10 to the 23rd. If you have a mole of people, it means you have 6.02 times 10 to the 23rd. That's all that number means. It's like saying dozen in there. And because your atoms are so small, the mole is a more usable amount of the substance that you can actually visualize in there. So the molarity is going to be the number of moles of solute per liter of solution in there. So this is one of those things, you'll get to do those kinds of calculations in chemistry and math 108 in there. When you're having to make up solutions of medications or IVs in there, you calculate these out. But that's what, if they didn't explain to you what this idea of a mole was, comes from chemistry, and looking at a mole of the atoms is 6.02 times 10 to the 23rd in there. And what's nice about the mole is numerically, it's the same as the mass of one atom. So if you look back at that carbon, and you had that decimal point in here. This is the mass in AMUs of one atom of carbon. It's also the mass in grams of 1 mole of carbon in there. And so it just works out nicely when we use moles. And that's how they came up with that number of moles in there, was through mathematical equations to find this, that you get to use this same number for both. You never have to memorize them because they're on the periodic table, and it works for both in there. So the molarity is a way of giving the concentration in chemistry where you get to have a specific number for it. And I think we're going to stop there today. We have 10 minutes left, and acids and bases are not the kind of thing that I want to tackle in 10 minutes.